Yeah, so sorry to inflict stuff on you twice today. And right. So again, I'm not quite sure how many people are going to be interested in computational complexity, but you're going to get it anyway. So because that's what I was asked to do: algorithms and complexity. So we've had algorithms. The reference I gave earlier to these ETH lecture notes, which you can get to from my webpage, Chapter 2 will cover most of it. At some point I'll go off at a tangent, but I'll give you the reference for that. So, right, I guess everyone knows it's the end of the day, so we have to keep this simple. So everyone knows MP completeness already, so we'll just amble through that. NP completeness applies to decision problems, yes/no problems. So once we've recalled the definitions and how it all works, which I guess is vaguely familiar to everyone at the, from Scientific American or whatever, then we'll go on to see, we'll examine what we need to add to it to get a theory of the complexity of counting. So, right. So let's go. So let's have a look first at classical NP completeness. So this goes way back to late 60s, early 70s, I suppose. So what are we trying to do? So in part 1, we saw that there were just a handful of problems which we could solve efficiently, always exactly, by reduction to a determinant. And there were obviously many other things we'd like to solve, but we don't have efficient algorithms for. We moved the goalposts. We looked at getting solutions with small relative error, and we saw that we could do a wider range of things, but still not as many as we'd like to do. And outside of that, many counting problems which, so we could do, for example, the ferromagnetic Ising model efficiently, in some sense. But, for example, we don't know how to deal with the Q-state ferromagnetic Potts model for Q greater than 2. Okay, so lying outside of what we're able to do, there's still a lot of stuff, particularly in the exact case, where almost everything is outside what we can do. Right, so we want a theory that kind of explains what things are intractable and why they're intractable. And in the classical world of decision problems, so this is arising out of logic, you've got instances, yes, and the question is yes, no. Given a graph, does it contain a perfect matching? Given a graph, does it contain a Hamilton cycle? Given a conjunctive normal form formula, does it have a satisfying assignment? So it's dealing with those yes/no problems. So it's formalized. So a problem in this classical theory is just a predicate on sigma star. So you have you choose an alphabet sigma, and you encode, it could be binary, say 0, 1. So encode all of your problem instances in binary, and you're going to encode problem instances as sequences of characters. So, for example, a graph, you'd express it somehow as an adjacency matrix and therefore reduce it to zeros and ones, then kind of linearize it. So let's call that predicate pi. So it's just it's a yes/no thing. So that's that. So for example, so let's take as our examples has a perfect matching. Oops. And has a Hamilton cycle. Now, these are two different kinds of problems because this first one has an efficient algorithm. So given a graph, we can very efficiently find, it's not easy to do, but with the right technology, you can find whether it has a perfect matching, whether it has a diamond cover. Okay? Whereas this one seems to be a much harder proposition. We don't have an algorithm which, given a graph, finds a Hamilton cycle in it. So it's that distinction we want to draw. So how is this done? So you need a notion of tractability, if you like. This is the class P. So we single out, and this is kind of very rough and ready approach. We single out those predicates which can be computed in polynomial time. So P is the class of predicates computable in polynomial time. Of course, we should sort of, to make this completely formal, we should have a formal model of computation, which is usually the Turing machine, but just imagine program. You've all written a program, so just think of a program. Computable in time polynomial, in time polynomial in X. Well, they should say predicates pi such that, sorry, it's getting late, such that pi of X is computable in time polynomial in the length of X, right? Because, so that seems to be the basic distinction we can make, because of course any reasonable decision problem is going to be solvable in exponential time, because usually we have available to us exhaustive search. We can always go through all the subgraphs and see if they're Hamiltonian. We can go through all of the assignments to the variables of formula, see if it satisfies it. And so that's an exponential time. So what's efficient? It should be substantially better than exponential, and we take that to mean polynomial. So you can pick holes in this and say, you know, if that polynomial was a 10th power or even a 5th power, that's not all that efficient, but you know, it's a start anyway. So we know by constructing algorithms that certain things like has a perfect matching are in P. So that first one, so perfect matching. There exists perfect matching is in this class P. Now we'd like to say, so this is the Holy Grail, that has a Hamilton cycle is outside P, provably, but that's beyond what we have at the moment, so we have to kind of sidestep that issue somehow. And go instead for, so this is what NP completeness is about, is to go for a relative result. So we have to introduce, we introduce a sort of a class which looks a bit strange usually because it's defined in terms of non-deterministic Turing machines, which is a sort of physically unrealistic model of computation. And I don't want to talk about non-deterministic machines in any case. So we'll kind of go at things a little slightly different direction. So we introduce a class NP of predicates pi, which are the following form that you can express in the following way: that pi on some input, some graph. This is true if and only if there exists another word, W, such that some other predicate, which I'll call chi for some reason, is true, and this witness, I call this W for witness, and W is less than, the witness isn't too big, so it's polynomial in the length of X. So NP so sidestepping non-deterministic Turing machines, we can think of it as the class of predicates you can express in this way, where this chi now is polynomial time. So these are things which are not necessarily themselves polynomial time, but can be expressed in the form of a witness checking predicate in such a way which is easy to compute, and can be expressed as a search problem where you're looking for a witness to some property which is itself easily checkable, and that witness is not too big. So just to perhaps we ought to go back to our examples. Has a perfect matching is in NP because the witnesses range over subgraphs. X is a graph. Witnesses range over subgraphs. And the checking here is just, given a graph and given a subgraph, is it Hamiltonian? And obviously the subgraphs aren't very big. So the polynomial is just linear there.
What's that word you're saying all the time? Witness? Or what
Witness.
Witness. Like
Yeah, okay, so there's a robbery in a bank,
like
and somebody observes it happening. And so that subgraph is a witness to the fact that a Hamilton cycle is a witness to the fact that the graph is Hamiltonian. I mean, it's almost a
just wanted
tautology.
to be absolutely sure that you're not saying witness index or something.
Yes, no, this is the 5 o'clock talk. This is the no-brainer one, right? So, yeah, and the second, yeah, we've done the second one. So you can see that almost any. Of course, there are decision problems that lie outside this class, but your bog standard decision problem can be expressed as a search. So for something not to be in this class, it has not to have witnesses. So it's a problem where even when you're given the solution, you can't recognize it as a solution. So well, these exist, but the vast majority of things are in here. So so this is this class contains almost everything in the way of decision problems, and in particular it contains things we don't know how to solve, so we believe that it's bigger than P. So it includes P, so the idea is to proceed under the assumption that it's strictly bigger. Sorry, this is sort of complexity 101, so it's going to bore a lot of the audience. Rigid. Proceed under the assumption. This is the idea. That P is strictly contained in NP. And if we do that, then we can make some progress. How we exhibit predicates which are the hardest ones in NP, in a certain sense. And if we can exhibit things which are the hardest ones in NP, then assuming NP is bigger than P, those hardest things will themselves be outside P. So the only thing we need to do to complete the theory now is to say how we're going to identify the hardest things, which I have to squeeze into this last. But it's just, so this is the last element is polynomial time reducibility. So we say that pi, this is one predicate, is poly time reduce. So this is, again, this is all very impressionistic. We're not going to have precise definitions. Reducible to, let's say pi prime is polynomial time reducible to pi. If we can compute pi prime in polynomial time. So by dear. I hope I'm still that's still active.
Very robust.
Yeah, good. It better be. So if we can compute this, so we have a program for pi prime which runs in polynomial time given an oracle for pi. So I would almost say subroutine here. So suppose you had you're given a little subroutine that computes pi for you, but I'm using the word oracle because you're having it for free. When you call this thing, you don't count the time it takes to compute anything. Imagine that's just a black box that in one time unit gives you back solutions to this problem pi. So I'll call it oracle because it's magical, right? So if I could if I can compute pi prime in polynomial time given such an oracle for pi, then I'll say that pi prime is polynomial time reducible to pi.
Does it make any difference if you say that the oracle costs 0 or costs 1?
No.
I mean, there'd be no situation where you'd want to call the oracle exponentially many times.
But you've got to use, I mean, it makes a strange model, but I've got to use the answer from it. Surely that's going to take some time. So I think I prefer to charge 1 for it, just to play safe, just in case there's some pathologies. There. Now, actually, here in the standard theory, actually you're only allowed, the way reduction is defined, you're only allowed to use the oracle once, and then only right at the end. And you have to accept its verdict as the one you're coming to. So this is Cook-Karp reducibility. So all, but this is just historical, and it's I don't know, it's just, it works, and it was how things were set up in the beginning. So if you open a textbook on NP completeness, this is the way reducibility will be defined. It will be that you do a polynomial amount of computation, you figure out an input to pi, you call pi once, and if it says yes, you return yes, and if it says no, you return no.
And that's equivalent to the more general thing?
No, it's not known to be. So
because that's so
that's a more subtle question than whether p equals np, which we don't know.
But that's such an unnatural definition, and this seems much more natural. You can call the oracle any number of times you want and use it how you want.
But it's but I don't think there's any known example where you can that extra generality. The only reason I'm pointing this out is that when we go to counting, it's going to be apparently crucial that we work with a more general notion of reduction. So I think this is a historical accident that it was defined this way, and well, that may be an accident. It's probably there's something real in the fact that this is enough for decision problems. That is somehow a statement about the world of decision problems, which does not seem to be the case. So this is why I'm sort of banging on about this, because even if people know about NP completeness, they may not realise that in order to go to counting, we need the more general notions. But for sure, it's not known whether Turing. So if you're allowed to call the oracle as many times as you like at unit cost, that's Turing reducible, and it's not known to be more powerful in this context.
And you say counting problems will use Turing reducibility.
We're going to use Turing reducibility because I'm not going to do any reductions, but it turns out that inevitably, in the more interesting ones, they always rely on polynomial interpolation. They always almost inevitably rely on constructing many problem instances whose solutions represent the values of polynomials at many different points. And by interpolation, you acquire a value that you're interested in. Now, sometimes you can take those many problem instances, and package them up as a single instance. The problem may be, it may be that certain problems, like perfect matchings, I don't want to come to a judgment on just now on this one. It may be that if you have a number of graphs, and you want, you've got some function of the perfect number of perfect matchings on those various graphs, it's possible that you can package up that function as the number of perfect matchings on a single graph. That will be possible in some circumstances, but apparently not all. So somehow you have a more general notion of reducibility, and it's just for the pragmatic reason that interpolation seems to be the main tool. Okay, so that's basically it. So just to complete this, I haven't got any more space left. NP complete just means that you're in NP, and well, I should really write it, shouldn't I?
You're allowed to use another black.
Yeah, but I was going to sort of make this. I was going to be really fancy, and this one was going to correspond. This was going to be all the counting analogues of that. Okay, so NP. So NP complete. So pi is NP complete. Just means it's in NP, and for all pi prime in NP, it's the case that pi prime is polynomial time reducible to, let's have a symbol for that phrase. So it's a hardest problem in NP. Every other problem in NP is reducible to it. So any other NP problem can be coded up. So to say that satisfiability is NP complete is saying that any other NP complete predicate can be any instance of it, of a problem for another predicate can be coded up as a CNF formula such that the answer to that decidability, so that satisfiability of that CNF formula is equivalent to decidability of the original predicate.
And there you're using the Cook-Karp definition.
Yes, so if to get the normal definition of complete, you would have to use Cook-Karp reducibility, and it's not known whether Turing would give you. It could conceivably give you a larger class, because it's a weaker notion of reduction. It's less demanding,
Right.
but that's not okay. But anyway, this has got no relevance to the topic of this program, so we have to move swiftly on to the actual thing, which is what does this look like? Of course, this is only going to exactly correspond once I move the board up. And it's going to be amazing if it does correspond. So now, what's a problem? Problem is it's a function from encodings of graphs, say, to natural numbers. And of course so there's various inelegancies, like actually you want to talk about computing partition functions and things, and where you have to sort of clear denominators, and so to get it into this framework. But anyway, just think of a straight, for the moment, think about a straight combinatorial counting problem. So, of course, we're talking about how many perfect matchings, and how many Hamilton cycles. Right, tractability is pretty much the same. So again, the notion of tractable will be polynomial time. But the class P is so much historically a class of decision problems that people tend to talk about FP. So this is just the class of functions computable in polynomial time. So you think in the Turing machine world, you're using the Turing machine as a transducer rather than just as a decision machine. And of course, from part one, we have examples. So we know that perfect matchings in the planar case is here. So an example would be so perfect matchings, number of perfect matchings in a planar graph is in this class.
Mark, the output number, the value of the function is output as a binary string, I guess.
Yeah.
So any counting problem whose value is something like e to the n is automatically not in this class, right?
Yes,
because it's a non-polynomial
you'd need to introduce your own tailored setup to talk about that. Yeah. I mean, you could do it. I don't know whether anyone's had that. Right. So let's have. So then, what do I want to say? So now we want an analog of NP, and that's number P. So number P is the class of functions sigma star to n, expressible class of functions f, expressible as, and we just take this on board, except that we're not interested in whether there exists a witness, but how many there are. So that carries across pretty easily. So that's the number of witnesses. So that's all number p. Oh, so some sharp p, number p. There's not. It's not uniform.
That's
How
sharp
people.
NP, isn't it? That would be sharp NP.
Sharp. There is a sharp NP.
What is
What's that? That's where you replace. Oh, let me finish this. Where again? Then I can tell. Then I can say, where chi is in p. So the witness, obviously, you're counting witnesses where the witnesses are easily checkable. That the class sharp NP I have seen occasionally, and it's used for the situation where the same definition but with chi is in NP. So it's, for example, counting Hamiltonian subgraphs of a graph. Right, so if you can get your brain around that one. So it's so you're taking a graph, and it's not a very. It's not. I'm not saying that you don't see. I'm going to rub it off as soon as I put it down. But you don't see sharp NP very often, because probably if the one that I've given you is a typical problem, it's perhaps not that relevant in practice. But that would be a valid one. You're taking your instance is a graph, and I ask the fascinating question: how many subgraphs of that graph are there which are Hamiltonian? And the witnesses are the subgraphs, but in order to check whether the graph is Hamiltonian, you can't do it within polynomial time, apparently. So you need an NP witness checker. But it's not a place. I mean, complexity theorists go here and worse places, but I want to keep this on a more practical level. I want to maintain. I want to have things which sort of actually correspond to something out there, hopefully.
So what is so special about the definition? Can't you convert any polynomial type algorithm to some witness algorithm?
You
there
can,
are-
yeah. So that's why P is contained within NP. You could certainly.
No, I'm looking at the definition here. This is polynomial time, right?
So this is, I'm saying any function you can express as counting so for example, number of Hamilton cycles in the graph. So the witness checker is, so X is a graph, W is a subgraph. This witness checker checks whether the subgraph is Hamiltonian. And so that, I mean, that's very unlikely to be a polynomial time problem, because even knowing whether there's one Hamilton cycle is hard. So counting them is likely to be even harder.
So in other words, you're saying FP is a subset of P.
Where FP is functions.
Not the
and,
same kind.
yeah. I'm just being picky about the types of these objects. Sort of. Yeah. And so we're going to proceed under. We're going to assume that FP and P are the same, right? Is strictly contained within. We're going to assume that there are things expressible in this form, counting witnesses, which are not polynomial time. And now we need to, as before, we need to identify the hardest things within number P, and we do that by reduction. But here, actually, I'm going to use I'm going to use what I actually wrote down here. So I'm going to use which is called Turing reduction.
Sorry, Mark, one more question. If P is not NP, then it's automatic that FP is not.
No.
Not even.
No, this thing could be this could even if that collapsed, even if
No, I'm
You
I'm
see-
saying the converse.
Oh, okay. If that collapsed,
If P is not NP, as we believe, then certainly this
Yes.
is not true,
Yeah.
because this is even harder.
yeah,
But it could be the decision problems collapse
Yeah.
and counting problems.
that's
collapse.
right. So even if it turned out that deciding whether a graph has a Hamilton cycle is easy, against all expectation, it could still happen that counting them all is a hard problem. That's consistent within the theory. Bill.
So I think you said a minute ago that P and FP were the same.
Well, there. I mean, that's just.
But you didn't mean that as. You
This
really
is-
mean that.
I mean, this is just function. P contains functions from sigma star to 0 to true false, and this contains. This is function. Yeah, this is going to be functions to more general functions, in particular to n, shall we say, just for the sake of.
But
Definitely.
perfect matching is in P and it's not in FP.
This is getting into a very semantic kind of area. This is,
No, it doesn't sound like semantic to me. I don't mean it semantically.
I mean, usually-
there is a polynomial algorithm.
usually the
to decide
things. A
if
lot of people
graph-
don't even distinguish these two, so I'm regretting even.
But
No,
it's
no,
given-
that's not what I mean, Mark. I mean, there is
Hmm.
a polynomial algorithm to decide if a graph has a perfect matching,
Mm-hmm.
but there isn't a polynomial algorithm to count perfect matching.
That is indeed the case, right? But you're jumping one blackboard ahead when you.
No, but that's why I think P is not equal to FP.
Oh no, that's a different. No, your assertion is there are witness checkers, chi, for which the decision version, the thing that I get from this expression here is in P. Perfect matchings is an example. But if I plug the same witness checker into this, I get a hard thing. Yeah, that's certainly true, but that's not.
No, I think what he's saying is.
That's true. That is a. I was going to come to that point in about 5 minutes, but we've come there already.
I think what
yeah?
he's saying is we could make these spaces right. Given a function f,
Mhm.
we can certainly define a predicate pi sub f as the predicate that f is non-zero.
Yeah.
Okay? And then it's clear that if f is in fp, then pi is in p.
Mhm.
The converse presumably is false, right?
Hmm.
Presumably there are functions f where pi sub f, for example, perfect matching, where
But-
pi sub f is in p, and we guess that probably f is not in
But
p.
I think the only way of making this completely rigorous is to focus on the witness checking predicate chi. I think this is the way to make precise statements.
Right, because it's possible
Because-
that everything collapses.
Because then you have a precise correspondence. If you fix chi, you then have a precise correspondence that you get a decision version out and you get a counting version out. And now you get fantastic open problems, if anyone's sort of like. For all witness checking functions, predicates, that yield NP complete problems over here, it's the case that those corresponding counting problems are number P complete. But this is just an empirical observation. And you could conjecture that every NP complete problem, decision problem, its counting version is number P complete. I would conjecture the converse, but it's consistent. And so a resolution of that would be fantastic. So
to go from
this is
the decision problem to the counting problem, there's not a unique way of doing it.
no, there is
Fix
not.
a witness
Yeah,
check
that's why I
pi.
would. That's why I would prefer to always talk about this thing here, because that makes a correspond. Because you might have some bizarre witness to Hamiltonicity, which yields a completely different. So is this finally getting toward Bill resolution of the Bill question?
You're asking me?
Because this is, but P and FP themselves, this is just the class of predicates computable in polynomial time. This is just the class of functions computable in polynomial time. So they're not, that's angels on a pinhead. But the distinction between these two things, this is quite interesting already.
Yes.
Yeah, it's fascinating. Yeah. Okay, so so now it all lines up. So you knew that stuff already. So now you know this stuff. And for those problems over here, so and also the nice thing about this setup is that we have now every decision problems and counting problems. Everything has two faces, so we can talk about the two views of the same thing. So now we can come back, given the structure, we can look at it in the decision world and the counting world. So Hamilton cycle, that's a typical NP complete problem. So it's probably, even in its decision version, it's probably hard, not polynomial time. Now for all, and now empirically, every NP complete problem you can think of, you can look at the proof of completeness, you can look at the reduction, you can tweak it and make a reduction over here. It won't necessarily work first time because just because you preserved one solution set. Here you only have to preserve the non-emptiness of the solution set. You don't have to preserve cardinality. So the reduction may not preserve cardinality, but usually you can patch it up in all known cases so that it becomes so-called parsimonious. It preserves the number of solutions. So it becomes a reduction which establishes number P completeness. So now so this is empirical. Every NP complete decision, and you want a sort of little slogan, every NP complete decision problem corresponds to a number P complete counting problem. So immediately Hamilton cycle is number P complete, ... But that is empirical. And it'd be nice, very nice to have a result that just said that automatically, so you didn't have to. But I suspect that there are totally bizarre things out there for which this is false. So bizarre witness checking.
Well, if you wanted to even make sense of it, you would first have to say, how, given a predicate, should I naturally define a function? I mean, in the case of Hamilton cycle, it's obvious that the function is count Hamilton cycles, right? But if you just give me a predicate pi, given a function f, I can define the predicate pi sub f, but the reverse.
Yeah, I don't want to go the other way. Yeah, to make a precise open problem, I want it that way around. Okay. Now the interesting point, so finally coming back, I think it was Bill pointed this out, that you can have things which are in P over here, but then when you go to here, they become complete in number P. So this was the breakthrough. So this was Valiant in about 78. Showed the permanent was so permanent of a matrix is, well, we sort of saw it already. Well, it's like okay. So permanent of a matrix A. So A equals Aij. It's just the sum over. So this is n by n. Oh dear, I'm not going to get to. So sum over permutations. I equals 1 to n. I sigma I. So it's like determinant, only you forget the signs. Another way of viewing it, it's the generating functions for perfect matchings in a bipartite graph with adjacency matrix A. And the Valiant result is, even if this is an adjacency matrix, even if this is 0, 1, that permanent, so this is the theorem, permanent manent is number P complete. It's in number P because the witnesses are perfect matchings, they're easily checkable. Knowing the number of perfect matchings in a bipartite graph is as hard as any counting problem. And yet, if you go to the decision world, determining whether a graph has a perfect matching is polytime. So these are the interesting, and these reductions are much more interesting and tend to use interpolation and sort of nice tricks. And it shows, and one interesting thing it shows is that Castellane technique for counting perfect matchings in a planar graph, it cannot, well, assuming this, it cannot extend to general graphs. So planarity was crucial there. So the fact that you can count perfect matchings in polynomial time in a planar graph, the planarity is somehow important because on a general graph it becomes a hard counting problem. And now this, I need to sort of shortcut a bit. So this theory has been worked out pretty much completely in the sense that, for all natural problems, we know either a polynomial time algorithm or we can prove number P completeness. So this is dramatically exposed. I have to get the Tut plane in. This is dramatically exposed in the case of the Tut plane, which many people here will know. Two-dimensional plane which plots out in a continuum various graph theoretic properties, like number of spanning trees, Potts model, ... And there, what happens is that, so it gives you a kind of continuum of a real playground of counting problems. And they're all number P complete, except on very specific points, like there's a point corresponding to spanning trees. In the planar case, there's a hyperbola corresponding to the Ising model, which is easy. So in almost any bipartite, planar, whatever the situation, you have a dichotomy. It's known precisely which points are polynomial time, which is very few, set of measure 0, everything else is number P complete. So that's a totally worked out theory. So what I really wanted to get onto was the stuff that isn't worked out. So is that okay so that's the world's fastest introduction to number P completeness ever.
So what is NP hard?
NP hard that just means you drop the, is it
Over
there
there.
still?
It's over there on the left.
Right. Yeah, you just drop this one. So if you have a problem which is not NP hard, yeah. So for example, counting Hamilton cycles will be NP hard, but probably not NP complete. Even after I've re-expressed it as a decision problem by saying, is the permanent of this matrix less than or equal to B? Which is probably what you're going to object to. Okay. Now, of course, now we have a wider class of problems which have efficient approximation algorithms. And what we would like to do is the same thing. In situations where we don't have an algorithm, we'd like to prove that there is no efficient approximation algorithm. And this is a much less well-developed subject. Okay, so at least I can say, so now we need an analog of P. So this is efficient, randomized. Oh, by the way, the reason we're going to randomized classes is, I guess, that almost all the known tractable problems are tractable via randomized algorithms, and we don't know deterministic ones. So because Markov chain Monte Carlo is kind of central, we don't know how to get round it. Simulating the Markov chain requires a source of randomness. And if you further restrict, if you disallow, if you look just at deterministic algorithms, you don't seem to get very far. So that's the pragmatic reason.
Are there any problems that are number P complete, but they can be approximated within 1 plus epsilon for all epsilon by deterministic algorithms?
There is an example, but unfortunately I forgot. I wasn't expecting this question. So
They're rare.
they're pretty rare, but I did find one, and I'm annoyed that I can't recall it now. There is such an example.
But there are problems where they're number P complete, but there are deterministic algorithms for getting within, let's say, a factor of 2.
I think once you're within a factor 2, you're almost certainly within arbitrary. For reasons I'm not going to get into, because I want to get something across here, because this is the open bit, really. Okay, so anyone who's familiar with the theory of approximate optimization. Okay, optimization problems. What's the biggest this? What's the shortest Hamilton cycle? What's the da 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 da? There's very well developed theory, and there are many grades. There's some problems in polynomial time you can approximate within 1 plus or minus epsilon to arbitrary epsilon. There are some problems you can get 1 plus alpha. For some fixed alpha, there's some you can approximate within log n, but not better. So there's a whole spec, very complicated and interesting structure. But for counting, for reasons I don't want to go into, there's just basically one notion, which unfortunately is called FPRAS. So this is a fully polynomial randomized approximation scheme, and we had the RAS already. So FPRAS for some function f is just the following. It's a randomized algorithm taking inputs x, which is the instance, the graph, or whatever it is, and an epsilon greater than 0, and returning a random returning result z, which is a random variable because it's a randomized algorithm, such that the probability. So we had this bit before, 1 minus epsilon times f of x is less than or equal to this. Z is less than or equal to 1 plus epsilon f of x is greater than or equal to 3/4, and which runs time polynomial in n and 1 upon epsilon. Okay, so that's the official definition. This is a very robust notion.
And time means worst case time.
Yeah, so this is worst case randomization entirely within the algorithm, not part of the product. So it's a worst case measure.
If you run over this polynomial time, you just have to give up and guess, usually wrong.
So typically it will be, you run a Markov chain, get a number of samples from a distribution, do some estimator relative to sample mean or something like that. Most of the time you'll get a good result, but occasionally it'll go wrong. So we have FPRASes for interesting situations like the easing model, ... perfect matchings in bipartite graphs, but linear extensions of a partial order. But there are many problems where we don't know approximation algorithms. So just to give you one which is uppermost in my mind at the moment, the number of perfect matchings in a general graph. So if the graph is bipartite, we have an FPRAS, but unknown whether such an approximation algorithm exists in general. Partition function of ferromagnetic pots with q greater than or equal to 3. It's 3. Q equals 2 easing model. We have an FPRAS. We have an approximation scheme of that sort, but it's very much geared to the special features of the easing model, and therefore that's... So it'd be very nice, and I suspect, well, I think most people think this is going to be intractable. I happen to think this one's intractable, but that's a kind of minority view, I think. But in any case, it would be great to have sort of some complexity theory that gives evidence for the non-existence of approximation algorithms for these things.
Is there a notion of completeness here?
Yes, so that's what you want. But you want a notion of, okay, so now we'll have to go into very hand-wavy mode. So,
Because again, you can't possibly hope to prove the non-existence of an F-class when you
Right.
don't even know whether P
Exactly.
is empty.
so what's going to be the technique? We're going to take the class of, so in a diagrammatic form, we're going to, that's your class that we're operating within number P, and we want to establish what are the hardest problems to approximate, and we only have one technique, it's reduction, so we want to identify some guy there, which is everything else everything in number P is reducible to it. Now this is exactly what we did with number P completeness, but with exact evaluation. But now we want reductions that preserve approximations, and that's the killer, because in the exact world, typically what you do is you create a whole bunch of problem instances, you give them to the oracle, and then you interpolate a polynomial. But interpolation it's not a stable business, and so even if these oracles give you approximate solutions, even quite accurate ones, your interpolation is going to be all over the place. So the main problem is that the basic techniques that give you so much power in the theory of number P completeness are just not available. So here, this is what I'd like to have is a more subtle theory of way of constructing these things. Now, there are many problems which are up here which have this for very trivial reasons. So just to take an example that I'm not particularly interested in is the number of, and then I do want to make reference to one independent sets in a graph. So that's a problem which is even hard to approximate. So it is true that everything down here is reducible to independent sets in an approximation preserving way. And it's almost trivial to do it, and it's got to do with the fact that this is the optimization version of this problem is hard. So if I have a graph and you want to know what's the largest independent set in it, then that's NP complete. And when you're in that situation, when you've got a counting problem which corresponds to an NP hard optimization problem, then typically these things are quite easy to construct. So it turns out to be quite easy. So given an instance of an NP complete problem, it's quite easy to construct a graph such that an approximate number of an approximation to the number of independent sets in the graph will tell you whether the formula is satisfiable or not, whether the graph has a Hamilton cycle or not. So there's a kind of class of very crude reductions that enable you to deal with counting problems which correspond to hard optimization problems. So that's enough to deal with that's enough for the hardcore gas model. That's just dead. As far in general, obviously special cases, Z2 may, for all I know, be achievable.
Are you saying that you do have what you consider to be a satisfactory notion of reducibility for approximation problems, but that there aren't very many cases where you can actually prove
the engineering
that the problem is complete in that?
Exactly. It's using. There's a satisfactory notion.
Is this the notion of RP?
This
Or
is
something else?
well, I don't know whether there's a. So I call it we call it approximation preserving reduction, and we studied it to a certain extent. I was going to give the reference.
But you have a class of problems that are hardest with respect to approximation.
Yes. So there are certainly things up here which will certainly contains everything which you recognize as being a hard problem in its optimization version, like independent set, like Hamilton cycle, like satisfying assignment. So those are all automatically excluded from this. And notice that we were able to count, we're able to approximately count perfect matchings in a bipartite graph, but that's fine because we can determine whether a bipartite graph has. I know I'm supposed to stop now, but since I'm carrying this paper, because it's got this is a desperate attempt to, because a number of us were there's a whole lot of things, counting problems where like this one, like perfect matchings in a general graph, that's a good one. Where we don't know how to get an approximate solution, but neither do we have a reduction. The reason we don't have that reduction is because the optimization problem is easy. There is a polynomial time algorithm, given the general graph will give you, say yes if there's a perfect matching. It's not easy, but there is. Okay, so this kind of crude reduction is not available. So in desperation, we started looking for, just forgetting about classes and just looking for problems that were related. And so we found a class of problems which are interrelated by approximation preserving reductions. And it was big enough that we thought, so I better get some, so this, I'm not going to say more than 5 minutes about this then, so. Oh, come last goes a green hill, right? And so this is in algorithmic 38. Okay, so this is a desperate attempt to get some kind of evidence for intractability. And so we noted that there was a bunch of problems which are all introducible by these approximation preserving reductions. So they're all of equivalent, either they're all efficiently solvable in an approximate sense, they either all have an FPRAS or they all don't have an FPRAS.
They might not be the hardest.
But they may not be the hardest. And this is opening up. This has been around a few years now, and no one's sort of managed to push these up or down. There's a suspicion arising that maybe this isn't a dichotomy. I mean, we used to dichotomies, right? Everything is, in practice, it's either in P or it's NP complete. It's either right at the bottom or it's right at the top. It's either FP or it's number P. But this is remarkable. And there's no reason to believe that that's going to be replicated in this approximate world. And maybe it isn't. Okay, so the only little bit of evidence that this class of things, I don't have time to write them down, but so the first, the prototypical problem is, for no reason other than it was the first to occur to us, was the number of independent sets in a bipartite graph. Right, but this, but because it's introducible with all of these other things, any of the others would have been equally decent as a starting point. Now, so this is the hardcore gas model when your underlying graph is bipartite. And it sort of escapes because actually the optimization problem is easy. If you want to know what the largest independent set in a bipartite graph is, it can be solved by network flow. So somehow we can't place it in that huge class, that we can't place it right at the top of number P. So that's one. There's downsets in a partial order. There's the Widom-Rollinson model. There's the Potts model. Oh, sorry, the Ising, Ferro-Ising with, don't know what to call it, with an external field that operates one direction in some places and another direction in another. Alan was telling, you were telling me that was actually a studied thing and thought to be more difficult. With
no, just say Ferro-Ising with General magnetic field.
General, okay, general
Magnetic field at both sides.
magnetic field.
Because what the point is, if the magnetic field was all the same sign, then you could make it equivalent to ferromagnetic using a model with one
Yeah,
extra
so
side.
if it's consistent, we can handle that there's an F-bras. But if you have the field acting one way on some atoms and the other way on other atoms, we don't know it becomes hard, but it becomes part of this class, right? So I'm putting this forward as a sort of, since we can't do the proper job, at least this is a class which contains some interesting problems, and they're all equivalent, and the more equivalent things we get into. But they do have a sort of independent existence. You can construct, sorry, I'm going over time. You can construct a well-defined class in here, which is, so that's FP, which is conjecturally somewhere in the middle. And I'm not going to define it, but I'll give you an example. I will write down, and this will really be the last thing, so I just want to give a flavour of how you could define a class of counting problems, which is somewhere between P or FP and number P, in a logical fashion. So I'll do bi-part independent set. What you have to do is you look at the graph, so the graph, this bipartite graph, you look at it as a structure in the logical sense. So it's a bunch of vertices. There's a predicate left, tells you whether a vertex is in the left or the right. There's adjacency. So it's a set, there's one unary relation, there's a binary relation of adjacency. Okay, and now you can define bipartite independent set. I mean, I'm not sure many people would be overjoyed with this, but this is the one thing in the audience won't be in the audience, the logicians. So we can define it to be so as counting unary predicates x, right? Such that the following sentence is implied by this model. So for all x, y in A, if x is on the left and x is adjacent to y, so y is on the right, and x is, two x's, that's bad. Okay, but the vertex x is in the independent set, then the other thing is not in the independent set. Now that looks a bit strange actually, because there's a different interpretation of x on two sides. So I have to now reveal that on the left, if x is on the left, then this predicate stands for x is in the independent set. This is why you need it to be bipartite. If x is not on the left, then this is going to mean, or if, let's say y, for consistency of notation, this means that y is not in the independent set. Okay, so it's a slightly bizarre encoding, but so we're saying that if x is in the left, and it's in the independent set, and it's joined to y, then y is not in the independent set. So that expresses that expresses the fact that x is a unary predicate which stands for an independent set in this bipartite graph. Now, you'll realise at this point why I don't want to give a formal definition of this class, but its salient features are that there is no second order quantification here. There is only first order quantification here, and it's universal. So that's one feature. And here, in general, this is a CNF formula in which every clause it can have arbitrary stuff in it, except that whenever you mention, there could be several of these, by the way, there could be several of these predicates here. Whenever you mention those, you're only allowed to mention them twice in the clause. Okay, this is sounding very natural, right? And you're only once positively and only once negatively. So here it's mentioned positively, and here it's mentioned negative. Oh no, it's not. X implies Y. Is not X or yeah. Okay, so here's the negative, and here's the. If I express that as a disjunction, that would be a negative occurrence. That would be a positive. Okay, so that's the whole deal. Is that it's first order universal CNF. At most one positive, at most one negative. These other things, you can refer to the model as much as you like, but when you refer to these things here, you can only use them once positively. That's it, very natural. Now, of course, you can instantly see that all of those fall into that class, and they turn out to be complete for this thing. So I'm hopeful that this is like a real concept, despite the fact it's looking like pretty nonsensical. But that is actually a real class of things there. And I conjecture that it's not FP. And so if we were, so I call this, we call it, everyone has to take the blame for this, restricted horn pi 1. So pi 1 is for this universal depth 1, and this is restricted horn. It's like a Hall clause, except it's even more restricted. So it's called RH pi 1. And these are all complete for RH pi 1. And so if we were prepared to accept that RH pi 1 contains some hard problems, then the payoff would be these would be now not approximable in polynomial time. So, which is something we don't know without any such assumption. So that's probably getting a bit exotic for the time of day, I think. I'll finish there. Yep. Hello.
You're not going to talk about phase transitions between various kinds of problems?
No. No, people start throwing stuff at me if I started doing that. Yeah, no, this is supposed to be complexity. Well, okay, complexity is related to phase transition.
Right, I mean,
Yeah,
because there are these issues where mainly physicists have been looking at satisfiability problems where depending on the values of some parameters.
Yeah, no, that's something I wouldn't dare touch. No,
not so hard problems. In the sense that
I know people who've spent months coming to terms with that, so I know. Yeah. And a bit,
any idea about the ferromagnetic flux model? I guess as a random cluster model with Q between 0 and 1?
0 Q between 0 and 1. Where is that? Well, if you tell me where that is on the tuck plane.
The hyperbola is
the hyperbola,
0 and 1.
It's 0 and 1.
Oh, I see it. On the tuck plane.
Yeah, everything I have to translate everything to the tuck plane. So H1 is easy, obviously, and then you're going below that. You're going into an unknown. That is precise. That is an unknown region. Yeah. Yeah, of course it's why you're asking. Yeah, nothing is known. Nothing is known in that neck of the woods. Bill was at his hand.
I don't know whether it's a sensible question. Suppose I give you a matrix with variables, and I'd like to know what its maximum rank is, so the real variable.
Okay.
Would that
So
fit?
maximizing over
Or real number.
the real numbers, yeah.
Would that fit anywhere in this structure?
So it doesn't naturally fit into one of these, does it? Is the answer? The answer is presumably it's polynomial time, yes.
No, it's a no.
Is
Is
it
that-
kind of a matrix of real numbers?
With variables in.
Oh, there.
Oh, this is rigidity, is it?
Yeah.
Yeah.
Oh, you mean a matrix of polynomials with real coefficients?
Yeah.
Oh, polynomials, yeah.
Or linear functions of n variables.
With, say, rational coefficients.
Yeah.
And then you want to know its rank.
Well, no, it's maximum rank overall. So there's an easy random algorithm. You just put random numbers in, work out the rank.
Oh, it's maximum rank when particular real numbers are substituted for the variables.
Yeah, so random real numbers will give you.
Generic,
Yeah.
generic set, so you just do it a bunch of times and take the biggest one, right?
Yeah.
High probability,
Yeah.
got it.
Yeah.
Unless your sample space is on a hypersurface, which has measure zero.
Yeah. So that's a quintessential example. What very often, if you have a randomized algorithm, you could de-randomize it at some cost, intellectual cost. But this one is not known. Yeah, that's right. So that's a dramatic example, really, because the randomized algorithm is trivial, and there is no known deterministic. Yeah.
But it wouldn't fit into the FPRAS terminology.
No. Yeah, so this is a decision problem. That's essentially, or an optimization problem. So.
Well, that's it. Good, thanks.